Okay, good morning everybody, and like the slide says, I'm Rami, and I'm working at Taboola, which is one of the largest recommendation systems in the open web, which means our scale is quite big. We have hundreds of services in production, ranging from a few cores to hundreds of cores, from hundreds of megabytes of heap to terabytes of heap, and yet at the end of the day, we're all just backend engineers, and two things life scare us the most. One is front-end development, and the other one is out-of-memory exception. And this is really shit. So my goal is by the end of this session to make sure that the next time you see an out-of-memory, you stay calm and take a dump, heap dump. But before we talk about heap and all that, wait. Okay. But before we talk about all that, let's talk about why people write in Java. I mean, it's not the fastest of languages. For example, Red Panda is a Kafka port written in Rust, which is almost 10x faster. There is CLDB, which is a Cassandra port in C++, which is almost twice as fast. Just the runtime itself is in the hundreds of megabytes, and it's just really, really old. And yet, it's consistently the most common programming languages out there. And if you look at the list, so Python is not really a language, okay? Yeah. And, okay. And C and C++, yeah, I'm not going to argue with the White House. And yet, so what makes Java so popular? So if you look at Wikipedia, there are many reasons, but probably the most important is just it's easy to write code in Java. And the reason why it's so easy, it's because it does memory management for you. Does that mean we don't need to worry about memory management at all? We'll see. So there's no way I'm going to be able to hold your attention for 50 minutes with just my looks. So we're going to do our own variation of the YouTube channel, Will It Blend. So welcome to the show, Will It Crash? In this show, I'm going to show you a real-life Taboola application, and you'll tell me if it's going to crash or not. So let's start. Will it crash? Okay, I'll help you. This is the first one. So around 3, the application restarted, and you can see the memory goes down. But then, surely and slowly, it continues to grow until it gets to some sort of a point. Then it plateaus. And probably here we saw an out of memory, right? Wrong. Before we understand why it's wrong, let's talk about what memory management really means. So if we try to simplify it as much as possible, it all comes down to two specific things. The first is reference counting. In the unmanaged world, when I allocate an object, I need to remember to free it, but exactly once. Well, in Java, you don't care. I mean, JVM does everything for you. The other one is a little bit more implicit, but it's directly connected, and that's heap ergonomics. In order to handle reference counting, the GC needs to manage what objects are alive and where, which means the GC needs to be able to trace any object back to its roots, and if there is an object without a root, it will eventually clean it up. And the faster it does it, the better the GC is, right? And in order to do it the fast, GC would always try and make sure the heap is as compact as possible to prevent the fragmentation, to allow it to allocate big objects, and in general, to better utilize the L1 and L2 CPU cache. As an optimization, the GC will never return unused memory back to the OS. It will always strive to have full control of the memory and manage it itself. So let's go to the app from earlier. It's now clear why the memory is stuck at its maximum, right? Because GC never returns memory back to the OS. And if you look under the hood, that's what the OS is, but what JVM really does, we can see a different story, right? We can see the heap goes and shrinks like in a relatively regular pattern, and everything is okay. In fact, because we said that we prefer the JVM to have it all and be less dependent on the OS, we can actually tell the JVM to give us minimum and maximum heap at the bootstrapping of the application. That's maybe hurting a little bit the bootstrap of the application because we need to allocate more memory, but from then on, we should get better and more stable performance. In fact, we can even tell it to utilize the maximum amount of heap we want, and then again, the bootstrap will be a little bit slower, but from then on, will be much stabler and much faster. Okay, again, will it crash? Okay? And of course, it always does, right? And usually it will happen at 3 a.m., where I'm basically asleep. And the thing is, everything looks good, right? I mean, all pools look quite stable. So why did it crash? And the thing is, just need to know where to look. And if we look only at the code cache, we see around 3.5, we passed the 240 megabytes threshold, which happens to be the default size of the code cache size. And obviously, we can increase it to be bigger and solve the issue, but it does show us two important things. One, that even if the total heap used is below the size we gave it, we still need to look at the sizing of each of the individual pools. And the second is that even if the JVM does memory management for me, we still need to give it hints on how we expect our system to behave. But the thing with all these hints is that they completely change the way the application works and how we need to monitor it. Let's look at another example. Will it crash? So this time we have two applications, look quite identical. One is going to crash and the other one isn't. Can you spot it? Okay. In both cases, we're looking at the old gen and we see it gradually increasing, right? It doesn't look right. On the other hand, if you look even closer, we see that on the right side, we are using G1 GC, which, not to get into too much details, means it will prefer doing constant small GC processes instead of occasional long ones. When on the left one, we're using parallel old, which will do exactly the opposite. It will do no garbage collection at all until the entire heap is full, and then it will stop application and run full GC. So while on the G1 graph, such a pattern clearly means we have a leak, on the parallel load, it just means we didn't get to the maximum heap size. And if we look at a longer time frame, we'll see that indeed every few days we reach the total size, we run full GC, and everything will work okay. While on G1, we continue to grow until we explode. So let's do a short recap. We talked about how the JVM is greedy in its memory allocation, not letting the OS play around. We saw that the heap is actually split into multiple pools, and that you need to give it GC hints on how you expect your system to behave, and that choosing GC has a huge impact on your system and the heap pattern itself. But putting aside all these hints and configuration, if the JVM manages all object allocation for me, why do we still get out of memory? Why do we need to live in constant fear from the home killer? So let's talk about what is a Java memory leak. If you go back again to the unmanaged world, when I allocate an object, I need to free it, right? So the good news is, when we're talking about Java managed... Sorry? Thank you. So when we talk about the unmanaged world, after each time we allocate an object, we need to free it. And in Java, the good news, you don't need to do anything, because the JVM will do everything for us. So when we're talking about managed objects in the heap, managed objects, this basically never happens. So thanks to our GC, if I allocate an object, and later I don't reference it anymore, it will do everything for me. Eventually, we'll clean it up. So a leak, according to its traditional meaning, isn't really relevant when we talk about managed objects. But let's look at another example. We have here a map acting as a naive cache, and each time we call the JDev method, it will allocate another simple object. But because the cache holds reference to it, it will never be freed. So every time we call the JDev method, our heap will continually and gradually increase over time until we get out of memory. And while this is a dead simple example, almost all memory problems we have in Java are either heap being too small, or we still use some sort of a direct or indirect reference to our objects. Okay, so there are memory issues in Java after all. And let's assume we were talking about a more complex app with many lines of code, and all we had was just knowing that the app crashes every few hours. Now what? So I'm starting looking at the heap pattern, and even though we're talking about G1, we can clearly see there's an issue here. So what are we going to do? Well, we have a problem. But the nice thing about Java is that everything is traceable. I mean, if GC is able during garbage collection to look at the root of each object, if you look at the heap, you can do the same. So let's take a dump. Heap dump. So there are many ways to take a heap dump in Java. You can tell the JVM to do it for you on out of memory. You can trigger it manually via JMX and many ways. But let's use specifically JMap, which is a tool that comes baked in with the JDK. And given a PID, JDEM will dump the entire Java heap to a local file. Now, there are a ton of apps that you can use to open this HProfile, but we'll use Eclipse Memory Analyzer, also known as MAT. I don't know where the T is coming from. Anyway, once we give MAT the HProfile, it will analyze the object graph, which can take quite a long time. But when it's finished, it will also build an index. So next time we open the same file, next time it will open the same file to be much faster. And once it's done, it will show us a pie breakdown of the heap. And it will give us some good examples of what he thinks are the problems. So for example, you can see here it identified the hash map as being the potential leak, and it can even point us to where it's being created. And if we can even drill down even further, and we can see which is holding the reference to each object, what is its shallow size, what is the retain size, and all sorts of great stuff. By the way, Matt also supports having reported generated via CLI, so we can automate the process. And I can even do some slice and dice with some sort of a query language. Not great, but it is possible. So Matt is really nice and all, and being able to browse an entire heap is really powerful, but it obviously comes with a price. So why not always take a dump? So first, in order to take a dump, the JVM needs to freeze all threads so it can copy the memory. So during taking the dump, my application is completely in downtime. Second, you need to dump the entire memory to disk. So I need to have at least 3 disks as I have memory. Third, it's really, really slow. For example, taking a dump of an 80 gigabytes dump took me 15 minutes. But even after taking the dump, parsing it can be much, much slower, like an order of magnitude slower. And lastly, applications are usually more complex than what we saw here, and there's no single type taking the entire heap. So without looking at multiple snapshots and comparing them, not sure it will help us in us. So we need something much faster and much more accurate. So if we go back to JMap, we can actually tell it to not create a full dump, but just take a small summary of the heap, called histogram. The summary contains a list of all types of classes on the heap, and the amount of instances, and the total shallow size of each object. By the way, the weird-looking numbers here, the C and the I, are basically primitive types. So it's just a primitive char array, primitive int array, and so on and so on. So it doesn't give us the same breadth of data like a full dump, but it's an order of magnitude faster. It's only a few kilobytes in size, and in many cases, it's enough to give us a hint on what's the problem. In fact, it's so lightweight and so useful that we thought, how cool would it be if for every service in Taboola, I could just go to some endpoint and automatically get some sort of a metric over time with data. Let's see what we did. So every application in Taboola already reports metrics to Prometheus, so we have the wiring already set. We added a new endpoint using a Spring Actuator, which is basically just a management endpoint. Not getting into the details. And every time you call it, it will create a scheduled job that will every few minutes create a JMap histo, parse the data, and create from it some sort of a metric, showing the amount of instances and the total size. And then we can very easily see what objects grow over time in relatively low overhead. But because histo only gives us the shallow size, the objects will always be just Java classes, like char array or string and things like that. But we can fairly easily just filter out all non-Taboola classes and see where the leak is coming from. So for example, we can see the TRC video object continues to grow. So probably this is the leak, right? But is it really just the video? I mean, we only saw that the shallow size increased over time, but the difference between shallow and retained could be huge. So let's understand what's the difference between retained and shallow. So let's say I have this simple object. It has 3 fields. The first one is long, and its shallow size is 8 bytes. The other one is string, which is basically a reference to another object. It could be huge, but the shallow size will always be just a reference, 8 bytes. And the same goes for the map. The map could be huge, taking the entire map, a heap, but for the simple object, the shallow size is going to be only 8 bytes. And so the difference between shallow size and retained size could be huge, making it really hard to identify the leak source. So while we focus on the video object being the highest with the highest shallow size, maybe the issue was we're actually creating too many heavy objects. So we need a way that given a class or an instance to measure its retained size without needing to take a full dump. And by retained size, I mean the shallow size of the object and the shallow size of all its children. So challenge accepted. So measuring an object size on heap. Let's break it into 2 separate tasks. The first is we want to measure the shallow size of the object, and then recursively measure the size of all children. So how do we do that? So you can say, okay, I mean, why is it so complex? Just do some sort of a heuristics of each property you have, and that's about it, right? But the thing is, it's not accurate enough, because the JVM and the GC adds a lot of overhead inside the object, and there are some padding happening as well to make sure it's all aligned to 8 bytes. So we can do some sort of guesstimations, and there are some libraries who does it, but the more complex the object is, the less accurate it's going to be. And then we're missing the whole point. So we want something much more accurate than this. So let's talk about Java agents. So what is a Java agent? A Java agent is basically a simple Java class that you load in addition to your application's class, and it allows you to instrument your code. And many tools you use today already rely on Java agents. For example, New Relic, it uses Java agent to instrument your code and give you some performance measurements. Or YourKit, it does the same thing to give you track allocation data. So it's quite used and very, very useful. So let's look at how do we create a Java agent. So in order to create a Java agent, you need to just create a new class, add some meta-inf files, not relevant, but you need to implement 2 methods. The first is pre-main, which is going to be called before your application is loaded, and agent main, which is going to be called after your application. But more importantly, they both give us access to an instance of an object called instrumentation. This is where it gets really, really cool. Okay, I mean, cool. Okay. So there are a bunch of things you can do with this instrumentation object. The first one is you can create a class file transformation, which allows you to completely instrument your code and change it completely. You can register your class transformer on a specific class, and we'll show an example later. But more importantly, you can call the getObjectSize, which gives you the shallow size of the object. Boom. Since now we can calculate the shallow size of an object, we gave our best engineer the task to write a method that recursively iterates over all children members and calculate the size of all children. Okay, so we have now a method given an object, gives us a good estimate of this retained size of the object. Now what? I still need to get a reference to this object, right? Now, while it's not perfect, most components do originate from some sort of a Spring bin, right? So, if you call the Spring context and ask for a specific bin, we can actually tell it to give us the retained size of the entire bin and all its children. So all we need to do is just wrap this entire thing with some sort of an endpoint, and then we have the entire flow. So we could just take any service in Taboola, call it with a specific bin, and get a complete measurement of its retained size and all its children. Pretty cool. But okay, so we've run a histogram, and we looked for Taboola class. We found a suspicious candidate. We then used our new tool to instrument it and understand the retained size. So we think we have a good candidate. But now what? But now what? I still don't know where the leak is coming from, right? Just know that it's creating too many recommendation objects. Okay, but before we continue, I have a confession to make. I'm Rami, I'm in Taboola, and we're using Java 8. Yes. And the reason why I'm saying this is because the next few slides are Java 8 not safe. Okay, now we have it above us. Let's talk about Java Flight Recorder. So Java Flight Recorder is a low overhead event recording system that's baked inside the JDK. And its sole system is to create a mechanism that is so lightweight it can be always on in production. And it collects many signals from the JVM and provides visibility on profiling data like GC, CPU, memory, I/O, even exceptions, and whatnot. In fact, it's so useful that most profilers today support it in some sort of way. It also came with a UI, which is pretty cool, called Java Mission Control. And some sort of trivia, it was initially a commercial part of the Java, but in 2018, I think, in part of Java 11, it was open sourced. So now, if you're running before Java 11, you need to specify to enable it. But from Java 11 on, just enable by default. So again, there are many events that JFR gives you, but we want to focus specifically on old object sample. So let's look what it does. So basically, it just creates a simple reference queue with a default size of just 256 that randomly picks a weak reference to an allocated object. Let's see an example, okay? Suppose you have this example2 class that on its creation creates a singleton object. We'll store a reference to it. And then there is a method called good, which creates a new object called simple object and an int. Once the method is completed, obviously the int is going to be dead and it's going to be removed from the allocation queue. But every time you call the good method, we create a new simple object and so on and so on. So the more time passes, the object will come and go out of this queue. And the longer the JFR recording session runs, the queue would contain more long-living objects, making them a good candidate for a leak. So when looking at the results, we can actually split objects age into 3 use cases. Assuming this is the lifespan of our application from creation until it's out of memory. And this is the time frame we ran our recording. If you look at objects created very early on, those are probably not very interesting. There are singletons and connections and things like that. It's objects I expect to live for a long time. This is not a leak. And if you look at objects that created at the end of the recording, they are not interesting as well. Probably ephemeral, like an int or string or thing like that. What we want to focus on is the objects created in the middle of the recording. Okay? These have the highest chance of being the root cause of our leak. So let's look at what data we get from this event. So we get when the object was allocated. We get the size of the heap when this object was allocated, so we can correlate it to how much the heap is growing. We can see what thread created it and what is the stack trace that created it. And we can even add the flag called pass to GC root, which means before the recording completes, it will run full GC, and we'll see which object has the reference to this object. Pretty cool. So why not always use old sample event? So first, to be honest, you should. I mean, it's really cool. Just open a recording, wait for a few minutes, and use it. But it's still not perfect. Why? So first, not all of us are using Java 8 or 11, no names. But if our service is a little more complex and we have many caches, there are many objects that by design go and stay a lot of time on the heap. So the flight recorder might not get them, or just get a lot of these objects, which is not relevant. Or in a more general note, if I already suspect the leak is of a specific class or a set of classes, I can't really use it. I mean, I just want the JFR theoretically to just run on my specific recommendation object. So we need something much more curated to what we're looking for. So let's say I've used all the tools so far, and I'm pretty confident the leak is coming from Taboola recommendation. I just want to find who is creating this object, and then I know how to clean it. And if we go back to the Java agent interface, we said it allows you to define a class transformer file. Let's see what this object looks like. So there are many methods to this function, which are not less relevant. Let's focus on two specific. The first one is the name of the class. A single class file transformer can be registered on multiple classes. So we need to be able to understand on which class we're working on. And the other one is just the byte array of the actual class, the code. And the output of this method is, again, a byte array, the content of the class. Now, you can write your own code that passes the class file and do it, but there are many open source that does it for us. For example, we use Java Assist, which is an open source library. It allows you to very easily work with regular class constructs. For example, I can ask it to get us the list of constructors, methods, and fields. And then we can just ask it to insert our code before, after, or instead the existing one. So we used it to call our track object method that will keep a track of all stack traces created in this object. So eventually, again, we create an endpoint that, given a class name, will call the object tracker agent, instrument the relevant class, and expose some simple aggregation over time that show us the stack trace, or the average age, or the amount of objects, and who created this object. And this is really, really great, but it assumes that where the object was created is where it's being held. So for example, in this specific case, it's really easy, right? I mean, the leak is exactly one line underneath the creation. But what if we have some sort of a more complex example? Like only once in a while we register a metric on a specific key, which creates a lambda, and this is where the actual leak is. I mean, we have another GC root. In this case, knowing when the object was created doesn't really help us. We need something more smart. We need something that, given a specific instance, tells me who holds it right now. So let's look at Java Virtual Machine Tools interface, JVMTI. And this is now the heavy stuff. It's a native interface, which means C++ and stuff like that, less Java. But it allows you to have full control over the internals of the Java. It allows you to inspect and control the execution of the application. You can set breakpoints. You can tweak the heap. You can change the code. You can do basically whatever you want. It's the basic building block that most profilers and debuggers use today. And you can even use it to expose using JNI native methods. You can to trigger it from your Java code. And so there are many things the JVMTI agent can do, but let's focus on two specific methods. The first is follow reference. Given some sort of a root object you suspect your object is, it will call your code for each of the objects it's been held. Then you can see if your recommendation object is really one of the children. And if you don't have a root to start from, you can just call the iterate through heap, which will just give you a way to go through the entire heap. Now, it's not free, and you still need to freeze your application while you do this, but it's much faster than taking a full dump. Okay, so far we were talking about long-living objects and focusing on the old gen, which is okay, because most memory problems do eventually come from there. But it's not all. Like we saw at the beginning with the code cache example, we can have memory pressure because of basically any one of the pools in a heap. Specifically, let's talk about young gen or new gen. Again, not to go into too much GC details, but the vast majority of GC algorithms split the heap into at least two sections, young and old. And the reason is that the vast majority of objects are created die very, very young. So it makes sense to split the code into young and old, because if an object doesn't die young, it usually will die after a long time. And if you split it into young and old, the GC will need to look only on the young parts. Less memory, faster GC, we are happy. And much for the most part, the assumption is good that young objects die fast. It's not always the same, and it can sometimes kill us. Let's look at an example. So we start with this simple object from earlier. Each time this method is called, we'll create a simple object. It will start its life from in the new gen, but because the cache object keeps a reference to it, it will survive multiple GCs, and it will eventually get to be on the old gen. So far, so good. But let's look at the following example. Each run will generate 1,000 simple object instances, and only at the end of the method, they'll be released. This means that the new section of the pool might not have enough space to cater all these new objects. And while GC will try to clean it up and run multiple GC cycles, eventually they will survive all these cycles and will be moved to the old gen, even though they are really young, and at the end of the method they will die. So this will clear up the new gen, but will make it harder for the GC to clean up these objects, causing both larger GC overhead on our system, but it can eventually even kill us, the same way as a regular leak is. Just to show you how the impact on our production system, this is a real production service in Taboola, which does all the serving. And theoretically, the origin should remain practically basically the same. I mean, all requests come, do some allocations, and clean it up, right? And yet, when I took this service out of Balancer, meaning it didn't get any new traffic, all threads were idle, the impact on the origin was huge. And the reason for that was it had enough time to clean up all the junctions that had to be promoted to the origin. So understanding what allocations we do, even if they're short-lived, can have a huge impact on our system. But because we're talking about short-lived objects, none of the tools we talked about so far will help us. I mean, there's no GC root, there's no gradual increase over time, just the rate in which objects are born and die very fast. So there are many tools that give allocation insights. But let's talk specifically about AskingProfiler. It's a very popular open source low overhead profiler. And the reason why it's so low overhead is because it trades off accuracy over performance. It doesn't instrument our code and add some sort of a placeholder. Rather, it just sample our application and the OS perf events. And it supports of all kinds of cool features like CPU and wall clock profiling, and of course, allocation profiling as well. And the output of each of those profiling sessions is a flame graph. So what is a flame graph? A flame graph is a way to visualize how the cost is distributed among the different stack traces. The width of each of those blocks determines the proportion of time spent in these stack traces. Let's look for an example. So we can see that the yellow one is a little bit smaller and takes just 17% of our time, while the big one takes 25%. This is the actual code, the JT server. But what's interesting we saw here is that almost 7.5% of our time just takes on creating metrics. And so we just create a lot of work on our GC for no reason. So if we optimize this code, it will drastically improve our system. We will reduce 7% the amount of allocations, less GC, more CPU, we'll be happy. So of course, we wrap this entire thing with another Spring management endpoint, and it's even open source, by the way. And then every service in Taboola can just, in a single endpoint, call it and get an allocation or CPU profiling in a second. Okay. So up until now, we talked about managed objects, but we cannot talk about unmanaged stuff. So it's a big enough topic to discuss next year, just about unmanaged stuff. But let's give a small taste of it. So of course, any object that is not managed by the JVM, like files and sockets and things like that, we won't be cleaned by the GC, because GC isn't aware of it. But obviously, it's more complicated than this. In this example, we open a file, read for it, and that's about it. I mean, we don't need to close objects in Java, right? And yet, even IntelliJ is smart enough to tell me that I'm missing something here. I mean, the file reader object already implemented the destructor, and inside the destructor, it does all of the cleaning up it needs to do, right? So why do we still need to close? I mean, why is it important? Why all the Java magic doesn't happen here? And there are two reasons for it. First, destructors are expensive. They run as part of the GC process and can hurt the entire app because it needs to wait for the destructor to end. But the second one is that while GC will eventually call our destructor and free all the unmanaged resources, we don't really control when GC would run. And in the meantime, all the unmanaged resources continue to stack up, and the OS might kill us. Let's look at an example. So let's assume this is the XMX of our application, and you can see when GC starts to run, right? When we get to the maximum amount of heap, the parallel org will start running, and we'll clear everything up, and we'll look good, right? When as time goes by, we start running our code. At the start, we have 0 file readers and 0 open files. But over time, we'll call more file readers, which will eventually be cleaned. But for now, not yet. So we still have open files, more open files, and more, until eventually the OS might kill us, because GC is not aware of the OS, and the OS isn't aware of GC. But again, more on unmanaged next year. So let's do a short recap. So we saw many leaks. We used JMap to take a full heap dump, but it was slow and heavy, so we used JMap histogram and measure it over time. But it only gave us a shallow size. So we used the Java agent to calculate the retained size of the object, but it didn't tell us where the leak originated from. So we used Java Flight Recorder and the old object sample event. It was really great and really cheap, and you should use it, but it wasn't very effective in large systems with many caches. We went back to the Java agent and instrumented our code. It was nice, but wasn't helpful enough in more complex leaks. So we went all in and implemented our own JVMTI agent and hacked the shit out of the JVM. But eventually, it wasn't really an origin leak, just some threads spamming our young gen too much. So one thing is for sure, in C# it wouldn't happen. Thank you.